So here is the third installment of this lecture. This lecture has slightly longer than I had originally intended, so I keep each segment to about 20 to 25 minutes, just so the file sizes are limited. Anyhow, so as we were discussing, the main upshot of, sorry, this is not where I wanted to go. Yeah, so the main upshot was this. The ln lambda, where lambda is this comes from the integration of dB over B, okay, from some kind of B min to the dBi length, okay, and this lambda is what's called the Coulomb logarithm. Right, and if you adopt the minimum, the classical minimum, impact parameter, which is determined when you say that the kinetic energy, when you demand that the kinetic energy be equal to the Coulomb potential energy. In other words, delta V parallel becomes comparable to delta V perpendicular. I would urge you to verify that this is indeed so. Okay. Here, I would urge you to verify this. Okay. So it's an interesting piece of not that hard to do. Okay. So if you plug in this BCL minimum, it turns out that yeah. So in place of B min, strictly speaking, you really should be taking the maximum of the classical or the quantum mechanical values. But for the sake of argument, let's just say we just go with the classical value, and when you plug it in, this is what happens. It looks like. And recall this any lambda dE cubed. Okay, so this is where the whole Coulomb logarithm, the lambda essentially is some factors, order of unity factor. Okay, which is this 12 pi times 12 pi over Zi, order of unity of something like order of 10 factor, times this all important dimensionless number, like that, lambda dE. Okay, the number density of particles times the volume of a debye sphere, the total number of particles inside the debye sphere. Okay, now since the definition of a plasma, well, and so this is, they say since the definition, we have not yet come to it. This is the whole reason I wanted to have this lecture as a separate standalone thing, was to motivate where this lambda comes from. Now, so this is where it comes from. Okay, this is the Coulomb logarithm, and so for instance, typical magnetic fusion experiments in lab plasmas have any lambda d cubed about 1,000,000, and so if you take the Coulomb log of 1,000,000, it turns out to be something like 17. Well, not just 1,000,000. That would be 6, but you have to also multiply this 12 pi. So therefore, typical values for log lambda, this range from something like 10 to 20. And because the lambda appears inside the logarithm, the exact value of lambda is not very important. Okay, so whether lambda is 20 or 25 doesn't really matter. The log it's a log, so the difference between log 20 and log 25 is not much. Okay, so now what about it? Let's go ahead and do and say a couple more things. So we wanted to do this, right? The delta F parallel. Remember, that's where we started out. That's where this Coulomb logarithm made its appearance. The average force in the parallel direction. Okay, So the average force in the parallel direction, writing down the formula again, and so that would be this Coulomb logarithm which we've discussed, and the rest of it we've already written down, times ME times V parallel. And if we insist that everything inside this square bracket be called, it does have the dimensions of frequency, you can verify that, be called a collision frequency. What frequency is it? Well, it's a collision frequency, right? Then the collision frequency, which is a function of V, okay, can be it's just this right here, okay, and all of this can be between here and here is just a little bit of rearrangement, and I will avoid this because we've not yet defined the plasma frequency, but we will leave it at that. Okay, now the interesting thing to note is that the larger the Coulomb logarithm, the larger the F parallel, the average F parallel. Okay, so in other words, the better screened the plasma, the more the more the F parallel. Okay, and let me see if there's anything much more to say. Yeah, so this would be again for a single electron traversing through a background of, this would be this entire expression would be for a single electron, or a single speed electron. Okay, traversing and a background of ions. Why background of ions? Remember this, the whole cylinder thing that we drew, like that. Assuming that all the ions were confined within this cylinder, and the radius of this cylinder is the impact parameter. Okay, and now the next thing to do, the other important thing to keep in mind is that the force, which is really a decelerating force, it goes directly as ln lambda. Okay, so the better the plasma, the more the deceleration. And this is called goes by the name of dynamical friction in stellar dynamics, where you've got one star passing through a background of many other stars. Okay, and when you've got a star, when you've got many stars, okay, like that, and you've got a test star passing through it, what will happen is the gravitational interaction, the only interaction between this star and the background of stars is gravitational, right? So the gravitational force is also proportional to 1 over r squared, just like the Coulomb force. So the treatments are very similar. And so for a star passing through a background of stars, it turns out that the star feels a drag. Okay, the test star feels a drag due to what's called due to dynamical friction. Very similar to this. Very similar to the, and here the idea is that think of maybe a small iron marble passing through a sea of styrofoam. Okay, so there will be a very small excess. There will be a very small shall we say, the density of these particles behind the moving object will be slightly larger than the density of the particles in front of the moving object. Okay, and therefore the gravitational attraction due to the stuff that's piled up behind is more than the gravitational attraction due to the stuff that's piled up that the test star encounters in the front. And therefore the test star effectively feels a decelerating force, which is called dynamical friction, very much in analogy with Coulomb collisions. Okay. Now, the other, and I will close with this. The other thing to remember is that this entire treatment is valid for a single electron given a single speed, okay, traversing a background of an ion. The natural extension would be to consider an electron which has a distribution of velocities, like that. Okay, a velocity. So this is a Maxwellian with a well-defined average velocity. Okay, so this is the mean velocity right here, V parallel, okay, capital V parallel, and the rest is just the usual Maxwellian. So what you do is you expand this exponential in Taylor series, and so what you do is, in order to calculate the same quantity, the average parallel force, okay, what you do is, you carry out just like, what would be the average, so what you do is you carry out volume integral, and in order to do the volume integral, you do the same, d phi, integral of d phi over 0 to 2 pi, and this would be over, cosine theta, simply going by the fact that the V parallel is V cosine theta. All right, and the other thing, of course, is that you stick in V in order to, you are interested in the average V. So you stick in a V and inside this is a probability distribution function. So you stick in an extra V here, okay, and that is it, really. Okay, and you carry out the integration properly, yeah. So you see, if you look here, there's a V parallel already, and we are sort of loosely, we are interchanging between V parallel and V. It's pretty much the same thing for our purposes, because the V is taken to be pretty much V parallel. There's not much deflection, and therefore, since you're sticking in an extra V, in order to, what you're doing is you're just sticking in a V, FV dV, right, in order to calculate the average V. So you have an extra V here, and that's why you have a V squared. That's why you have a V squared here, and you carry out the integral, and you get the Maxwellian averaged electron ion collision frequency. Just like you had the collision frequency out here, you had a collision frequency for a single speed ion, right? For a single speed electron. Here, this is an average over all speeds as defined by the Maxwellian. Okay, and it's a slightly different expression. Okay, and from the collision frequency, you can calculate a mean free path, right? Given a typical speed, you can always calculate a mean free path. Given a frequency is simply a time scale. So given a speed and a time scale, you can calculate a mean free path. And so this is how you get a mean free path for an electron passing through a background of right here, what we discussed in the very beginning. This guy. You see, how do you define a mean free path? Well, the mean free path, because it's a succession of very small deflections. So you define the mean free path as that point where the deflection from the initial direction is 1 radian. And this is how this is the exact way of what we just discussed. Finished discussing is the exact way of doing this. You get a collision frequency. From that, you invert the frequency, and you get a time scale. And you have a typical. And since we are now talking about a Maxwellian, it makes sense to think about a typical velocity as a RMS velocity. And so you have an RMS velocity, and you have a time scale. And from these two, you can get a mean free path. Okay, so this is all. I wanted to stop here. I just wanted to give you a flavor of where the Coulomb logarithm comes from.